Hello class 12. The topic that we are going to discuss, as you can see written on the board, is Lensmaker's formula. Now this is one very important topic for you all, remember, in ray optics of course. Because we of course are going to do a derivation for the Lensmaker's formula, and this derivation is very important for you all. You all should learn how to get the Lensmaker's formula, that is, you need to learn the derivation. It's very important, but I tell you, it's not very complicated, because it starts with this equation. Okay, this is the equation that we derived for refraction taking place through a spherical surface. We did the derivation for a convex spherical surface. If you can remember that expression, and for this derivation of course you need to remember that expression, the relation that we got. Okay, and we start with that expression. So what we have is, we have a lens. Now talking about lenses, I should remind you, I should tell you that here in class 12, of course I'm not going to define the different terms related to lenses like the optical center, focal length, radius of curvature. Okay, these things we assume in class 12 that you very well are familiar with these different terms related to lenses. Furthermore, the different images that are formed in case of, here I have shown a convex lens, of course there will be concave lens also. So the formation of images in case of convex lens or concave lens for different positions of the object also, we assume that you already are familiar with. So I suggest you to give these things a look. First of all, the different terms related to lenses, and then after the formation of images, because that will help you a lot, remember. Now, here we have a convex lens, and what we are assuming is, we are assuming that there is a point object O at a distance U from the pole P1 of the first surface of the lens. So U is the object distance, and this U is measured from the pole of the first surface of the lens. Remember, a lens obviously will have two surfaces, or rather two refracting surfaces. So P2 is the pole of the second surface of the lens. Now, for all our study purposes, what we consider is, we consider lenses having small aperture. I told you what aperture is. Aperture is the distance between the two ends of a lens, or for that matter any surface. So we consider lenses having small aperture, although it does not look like that in my picture. And we also consider very thin lenses. Okay. Now what is the reason for considering very thin lenses? The reason for considering thin lenses is because the distances here, as you can see, these distances are measured from the pole of the first surface, whereas these are distances measured from the pole of the second surface. So if the lenses are thin, then the distances measured from the respective poles, it's considered to be the same as the distance measured from the optical center of the lens. Okay, this is the reason why we consider thin lenses, and therefore we consider, so to say, all distances measured from the optical center of the lens. Okay, so very important words. Thin lens means all distances are measured from the optical center, so to say, and all lenses have small aperture. Remember that. Okay, but before we jump into the considerations that all distances are measured from the optical center of the lens, we still, for the time being, consider that the distances are measured from the respective poles. Okay, respective poles, such that T is the thickness of the lens. For the time being, we are sticking to the measurement taken from the respective poles, and we are considering T to be the thickness of the lens. Alright, so O is the object, and we consider a ray of light coming from the object. Okay, now if there was only the first surface, of the lens. So to say there was no second surface of the lens, then of course the ray would refract and an image I dash would be formed over here. So we would get an image I dash if there was no second surface of the lens. Alright, so for refraction taking place on the first surface of the lens, I dash is the image, and you can see the distance of I dash from the pole P1 of the first surface is B dash. Okay, so for now we are considering refraction only taking place to the first surface. So for refraction taking place to the first surface, we can write eta 2 by V dash, where eta 2 is the refractive index of this medium, the second medium, which is the lens in this case, and eta 1 is the refractive index of the first medium. So the refractive index of the second medium divided by the image distance minus refractive index of first medium divided by the object distance is equal to eta 2 minus eta 1 divided by the radius of curvature of the first surface, which is this distance r1. Alright, so this is what we get, of course, the relation that we get for refraction taking place through a spherical surface. Alright, so let's call this our equation number 1. Let me write it this way since we don't have space. Okay, so this is for refraction taking place through the first surface. Now, since there also is a second surface, this ray of light, refracted ray of light on the first surface, okay, further undergoes refraction, and actually the image is formed at this point. I is the actual image formed when we consider refraction taking place through both the surfaces of the lens. Okay, so I is the actual image that is formed. Now, for refraction taking place on the second surface, we consider I dash to be the object for refraction taking place on the second surface. So, if I dash is the object for refraction taking place on the second surface, the distance of the object from the second surface, that is the pole of the second surface, is V dash minus T, where T of course is the thickness of the lens. And V is the distance of the image formed measured from the pole P2 of the second surface. Therefore, for refraction taking place on the second surface, we get, what do we get for refraction taking place on the second surface? We get eta 1. Now see, it's like now, since eventually the ray of light is coming out to this medium, to air outside, so air is the second medium and the first medium is the medium of the material of the lens. So eta 1, that is the refractive index of the second medium, divided by the image distance, it has to be, image distance is V, divided by V, minus the refractive index of the first medium, divided by the object distance, which is this V dash minus T. So V dash minus T. This has to be equal to the refractive index of the second medium minus refractive index of the first medium divided by the radius of curvature of the second surface. Now this is the second surface and C2 is the center of curvature for the second surface. So this distance is the radius of curvature of the second surface. So this is what we get. Now we apply our conditions. Okay. Now what are the conditions? The conditions are, of course, the lens has to be of a small aperture and the lens is a thin lens. Okay. So all distances measured from the respective poles, it's the same as the distances being measured from the optical center. So since the lens is thin, T is very small. So instead of V dash minus T, we can simply write V instead of V dash minus T. Now there's very small space My board is very small, so to say. Okay, I'm having difficulty. So, considering thin lenses, let's simply write this. Considering thin lenses, what we can write is, considering thin lenses, this expression can be written as eta 1 by v minus eta 2 by v dash is equal to, let me rewrite this as minus of eta 2 minus eta 1 divided by r. So this is, say, our equation 2. Now what we simply need to do is, we simply need to add these two equations, equation 1 and equation 2. Let me do the addition over here, okay? Let me keep my equation 1 intact and also my equation 2, of course. So let me do the addition here. Therefore, adding equations 1 and 2, we get, what do we get? See, this first term for the first equation and the second term for the second equation, they are one and the same, but this is with the minus sign, this is with the plus sign, so they simply cancel each other out. So let me straight away write eta 1 by v minus eta 1 by u. You can check the mathematics, okay? Please do check the mathematics yourself. So I can take eta 2 minus eta 1 common. So this is eta 2 minus eta 1. And what do we get inside the bracket? We get 1 by r1 minus, oh sorry, this is 1 by r2. Okay, so 1 by r1 minus 1 by r2. This is my equation. Alright, now I only need to tune this equation a bit. This is my final equation, so to say. Now, how do I tune this equation? What we do is, we divide both sides of the equation by eta 1. Alright, so dividing both sides by eta 1, what we get is 1 by v minus 1 by u is equal to eta 2 by eta 1 minus 1 into 1 by r1 minus 1 by r2. Okay, now what is eta 2 by eta 1? Eta 2 by eta 1 is the refractive index of the second medium with respect to the first, so to say the refractive index of the material of the lens with respect to the surrounding medium. Alright, so therefore, let me erase this also now. It's not very important for me since I've already added. Let me erase my equation number 1 also. So finally what do we get? Therefore we get 1 by v minus 1 by u is equal to eta minus 1, where eta is the refractive index of the material of the prism with respect to the surrounding medium, into 1 by r1 minus 1 by r2. You can write that here, where eta is equal to eta 2 by eta 1. Okay, you can write that thing over here. Understood? Now, there is one thing that we can say further, and that is, for this convex lens, and this is a real image that is being formed, mind you. So, if the object is at infinity, if the ray of light or this object is at infinity such that the ray of light is coming from infinity, okay, then where would the image be formed? The image would be formed at the focal point of this lens. So the image, the final image would have formed at f, that is, this is the focal length, the image distance would be equal to the focal length. So let me call this our equation number 3. Therefore, equation 3 will become, or will be like, okay, will become what? U is infinite, so 1 by f for v is f, 1 by f minus 1 by infinity is equal to, the right hand side is still the same, no change whatsoever on the right hand side. Okay, let me erase this, you don't need this. Now 1 by infinity sum is 0, so this is equal to 1 by f is equal to eta minus 1 into 1 by r1 minus 1 by r2. This equation, let me call this equation number 4, is what is called your Lensmaker's formula. This gives us the relation, as you can see, basically between the refractive index and the focal length of the lens, and of course their respective radii of curvature. Okay, now why is this called Lensmaker's formula? This is called Lensmaker's formula because lens manufacturers, they use this very equation to make a lens of a particular power, that is lens of a particular focal length, using glass or using a material of a certain refractive index. Therefore, it is called the Lensmaker's formula. Remember that. Okay, so this is equation number 4. This is equation number 3. Now, from equation number 3 and equation number 4, you can see the right hand side is the same for both the equations, so we can of course equate the left hand side. But before we do that, let me write equation 4, or this equation is called the Lensmaker's formula. Remember that. Lensmaker's formula. Important. This is very important for you all. And equating equations 3 and 4 we get, so from equations 3 and 4 we get, what we get is 1 by f is equal to 1 by v minus 1 by u. Now this is another important equation that we get for lens. Okay, this is what is called the lens formula, simply the lens formula. This is your lens formula. Now this is exactly the formula that we have used in our experiments also. When we did UV method, okay, it is this formula that we used, which is called the lens formula, remember. Also for displacement method we use this equation. Okay, so two very important equations that we derived. One, the Lensmaker's formula, and the other is the lens formula. Now get one thing very clearly. Although we derived these two equations for a convex lens forming a real image, these two equations are true for convex lens forming a virtual image also. Also, the very same two equations are true for a concave lens also. Concave lens, mind you, forms only virtual images, whereas convex lens forms both real and virtual images. So these are the two important equations that we needed to derive. Thank you.